Hello everybody, welcome to the Mathematics for Programming course. In this video, I'm going to discuss the use of linear algebra for computer programming. So I'm going to cover a number of topics about linear algebra together with the code that can help us understand more about linear algebra. So how can we use linear algebra in computer science or computer programming? We can use the linear algebra topic in graphics, machine learning, data science, and scientific computing. Also, we need to use linear algebra to handle the multi-dimensional data, the transformations of the data, and even the optimization can be achieved by using linear algebra. So in this video, I'm going to demonstrate the Python code. We mainly use the NumPy library so that I'm able to use the linear algebra submodule coming from the NumPy library. So I'm going to use the linear algebra module in the NumPy library to handle the numerical calculations in Python. So the first idea to discuss is the vectors in linear algebra. So what is a vector? A vector is really a list of numbers that can represent a point or a direction in the space. So we can use x, y, z for the three-dimensional point. So we have three components, x, y, and z, and they are called components of a vector, okay? And a vector has a magnitude and a direction in the mathematical sense. So it has a length and the orientation. So we can treat a vector as having these two parts, okay? And how can we apply the use of vectors? We can use them in graphics. So for example, if we want to represent the positions and the direction or the velocity of some 3D object in a 3D space, we can use vectors to represent all these quantities. And in machine learning, we can create our feature vectors to describe the data points. So all the data points can be put in the form of a vector to represent the feature vector, okay? So for example, the pixel values in the image can be put in a vector to represent the features contained in the pixels, okay? And in physical simulations, we can use vectors to represent forces, velocities, and acceleration. So in 3D vectors, we can use the two coordinates to represent the vector. So we have the starting point x1, y1, z1, and the ending point with coordinates x2, y2, and z2. And we can use this formula to evaluate the length of a vector. So I just put the coordinates into the equation to get the length, okay? And we can also do vector addition. So we can add vectors, but the addition isn't like adding numbers so simply. We now add vectors. So how can we do the addition of vectors? We need to place the vectors head to tail and draw a new vector from the start of the first one to the end of the last one. So the first one is A and the last one is B. So I start with the starting point of the first vector, which is A, and then I will end with the ending point of the last vector, which is B. So A plus B is this one. So A plus B is obtained by adding the two vectors, and the resultant vector is just this one, A plus B, okay? And we can have scalar multiplication in vectors. So what does it mean by this multiplication? We just multiply the length of the original vector by a real number and keep the direction unchanged. So originally we have C, which is a vector, and if I put a scalar multiple called K before C, it means that the length will be altered by this scalar multiple, and the orientation of this new vector called KC will be unchanged. So the orientation of this new vector will be the same as the original vector C, okay? So that's the meaning of the scalar multiplication. We just change the length, but retain the orientation unchanged, okay? And for vectors, we can find out the dot product, which is evaluated as this formula, u dot v equals u1 v1 plus u2 v2 plus u3 v3. So when I have the vector u and the vector v, I have their components, okay? And then I can put the components into the formula to find out the dot product. So we have to remember something. The dot product is a scalar quantity. That's why the value here is a scalar value rather than a vector. So we can use two vectors to evaluate a scalar by using the dot product. Okay, so let us go to the Jupyter Notebook to see how we can implement the vector operations in Python. So here, we can do some vector operations. The first thing to do is to import the NumPy library as np. And then in the NumPy module, I can just use the array function to produce a vector by using np.array, and then I need to include the components in a pair of square brackets. Okay, and then I'm able to show the vector that I created. And how can I do the addition of the vectors? I can just use an ordinary plus symbol here, so that I'm able to get the sum of the two vectors. And when I want to do the scalar multiplication, I just need a scalar quantity, which is 2 in my case, and we use an asterisk to represent the multiplication. Okay, and then I've used v1, which is a vector, to represent the vector here. Okay, so that I'm able to do the scalar multiplication. K is now 2 and C is now v1. Okay, and if I want to do the dot product, I need to use np dot dot. Okay, so we have the function, and we put the two vectors to take the dot product into the np dot dot function, and then I'm able to get the dot product. So let us see the result of running the cell. Okay, you can see that I'm able to get the two vectors by using the numpy.array function, and then I do the element by element addition. Okay, so 1 plus 4 is 5, 2 plus 5 becomes 7, and 3 plus 6 becomes 9. And then I can go to the scalar multiple here. The scaled vector is just multiplying all the elements in vector 1 by 2. So I will have 2, 4, and 6 as the answer. Okay. And for the dot product, it is easy. I just need to handle the formula shown here, so that I'm able to do 1 times 4 plus 2 times 5 plus 3 times 6. So 4 plus 10 plus 18, I'm able to get 32 as the answer. So that is the meaning of the dot product. Okay, so we have learned some basic knowledge about vectors, and then we can go to another topic. The next one is matrices. Okay, so a matrix is a 2D array of numbers. It is used to represent the transformations, the system of the linear equations, or the data sets. So the rows and columns of a matrix would help us to define the shape. So maybe we can have a 2 by 3 matrix, which has 2 rows and 3 columns. Okay, so the first value represents the number of rows in this matrix, and the second number here is meaning the number of columns in this matrix. Okay, so we can have an example shown here. Suppose I have this matrix 3, minus 2, minus 4, and 1. So we can denote the elements of the matrix by using the row index followed by the column index. So we have this one. For A12, it is going to mean row 1, column 2. So the element in row 1 and column 2 is this value, which is negative 2. That's why I would say A12 is negative 2. And we can use this notation to represent other elements in the matrix. So A11 is number 3 because it is the element in row 1 and column 1. And we can say that A21 is minus 4 because it is the element in row 2 and column 1. And A22 is just equal to 1 by the same token. Okay. And we have a certain property called identity matrix, which is this one. An identity matrix will be having ones on the diagonal, which starts from the top left to the bottom right, and all other values would be 0. And the dimension of the identity matrix has to be a square matrix, so the two numbers here must be the same for an identity matrix. So if I say I2, it means that I have 2 rows and 2 columns, and all the diagonal elements would be 1, and the off-diagonal elements would be just 0. Okay, so this is an identity matrix of dimension 2. Okay, and note that for any matrix A times I equals I times A equals A. So the order of A times I and I times A doesn't matter, and the product of these two things would be just equal to A. So as long as the matrix multiplication can be performed, we can say that AI equals IA equals A. Okay, that is the property of an identity matrix. Okay. And how can we use matrices in computer science? We can use them in computer graphics. For example, we can do transformation matrices. That means the rotations, scaling, and translation. So that we can use the matrices to manipulate 3D objects. Okay. And we can also use the matrices to handle machine learning. So, for example, if I want to indicate the weight matrices in the neural networks, we can use the matrix format to help us denote the weight matrices, okay? And in graph theory, we can use the matrix to represent an adjacency matrix, okay, in order to indicate the connection of the nodes in the network, okay? So let us go to the other part, which is called the matrix operations. So for matrices, we can do addition and subtraction. What does it mean by adding two matrices or subtracting two matrices? It is just meaning the element-wise operation. So A11 is going to add with A11 of another matrix. So it is just doing the addition or subtraction of elements one by one in both matrices, okay? So 1 plus minus 5 is minus 4. Minus 2 plus 6 is 4. Minus 3 plus 7 is 4. And 4 plus 8 becomes 12. Okay, so I do the element by element operation. And we have to make sure that the matrices have the same dimensions. So when we do the addition or subtraction, we have to make sure that both matrices will have the same dimension. I mean the same number of rows and the same number of columns for both matrices. Okay, otherwise the addition and subtraction cannot be undertaken. Okay. If we want to do subtraction of matrices, it is using the same technique by handling the elements one by one. 1 minus minus 5 is 6. Minus 2 minus 6 is just minus 8. Minus 3 minus 7 is just minus 10. And 4 minus 8 is just minus 4. That's why I'm able to do the subtraction in this way as well. And for multiplication, we can separate the multiplication into two parts. One is by means of using a scalar, and the other is by means of using another matrix. So let us handle the scalar multiplication first. So the scalar multiplication can be used in transformations and neural network layers. And the scalar multiplication is done by multiplying each element by the same scalar quantity. So for example, if I multiply all the matrix elements by -5 before the matrix, I'm able to get minus 5, minus 10, minus 15, and minus 20. Okay, that is the meaning of the scalar multiplication. Okay, and let us go to the matrix multiplication. So how can we do the matrix multiplication? It is talking about a matrix multiplied by another matrix. Okay, so it can be achieved by the dot product of the rows and columns. So we have a row here, row 2, 3, and column 4, 2. So 2, 3 dot 4, 2 is able to help me get 14. Okay, 2 times 4 plus 3 times 2. Okay, so I'm able to get 14. Okay, that is the meaning of the dot product in this way. So A11 of my final answer would be evaluated from taking the dot product of the first row and the dot product of the first column. Okay, and for the A12 here, it means the dot product of the first row and the second column. Okay, 2 times 1 plus 3 times 3 equals 11. And for A21 here, it is obtained by taking the dot product of the second row and the first column. Okay, so I'm able to get 28. Similarly, for number 17, which is A22, I'm able to do the dot product of the second row from the first matrix and the second column from the second matrix. Okay, so I'm able to get 17 in this way. Okay, so in doing so, the number of columns of the first matrix is equal to the number of the rows in the second matrix. That means we can achieve the dot product by making sure that the number of columns in the first matrix is equal to the number of rows of the second matrix. Okay, otherwise I'm not able to produce the dot product because I don't have matched number of elements to do the dot product. So we have to make sure that my dimensions of the matrices would allow the dot product evaluation. Okay, now let's talk about the inverse of a square matrix. we need to use the matrix inverse to solve the system of linear equations. If I have this relationship called AX equals B, I'm able to use the inverse of A, which is indicated by the -1 power here, to help us evaluate the unknown, which is X. So this A is given, and X is the unknown vector to be found, and B is the solution vector. Then I'm able to use the matrix inverse to help us find out the original unknown back, okay? So suppose I have a matrix called A as this one, and X is the unknown vector, and B is the solution vector, which is equal to this one. And if I have this relationship, I can use the inverse of A to help us find out x1 and x2 respectively, which is just equal to 3 and -2 respectively. So I have to calculate the inverse of this matrix, 1 minus 3, 2 and 5, okay? So the analytical formula of finding out the matrix inverse is a bit complicated, but fortunately we can use NumPy to help us get the inverse easily. And how about the transpose here? The transpose is obtained by flipping the rows and columns, and this transpose is helpful to do data processing. So how can we get the transpose? We just flip the rows and columns. So originally the matrix has this row and this row, and now I turn the row into columns, so you will see that I have done the flipping by doing the transpose operation, okay? So I have to use a capital letter T in the power position of the original matrix to indicate that I want to do the transpose, okay? And we can talk about the determinant of a square matrix. How can we get the determinant of a square matrix? We can multiply the top left and bottom right elements and then subtract the product of the bottom left and top right elements for a 2 by 2 square matrix, okay? So if we have a 2 by 2 square matrix as this one, A, B, C, D, then it means that the determinant of this matrix is equal to A, D minus B, C. So this formula is just for 2 by 2 square matrix only, okay? For 3 by 3 or 4 by 4 and so on, we have to rely on other formulas that are a bit complicated to introduce here. Of course, we can still use the NumPy library to help us do all the determinants easily, okay? That's why we don't need to worry about the implementation analytically, okay? And for the orthogonal matrix, it has a property like this one. So not all the matrices are orthogonal. An orthogonal matrix has to satisfy this condition. A times A transpose equals A transpose times A equals I, okay? So if we have this property, then we say that this A is really an orthogonal matrix, so that we can see this example, which is an orthogonal matrix. So you can see here, I have this matrix, and this one is an orthogonal matrix because when I do the transpose and I multiply the transpose by itself, I will be able to get an identity matrix. And when I multiply A by the transpose of A, I'm also able to get the identity matrix back. So if you are able to check it out by using the multiplication rule and the transpose rule, you will see that in both directions, you will still get I as the answer. So that's why I would say that this matrix is really an orthogonal matrix, okay? And how can we apply matrices in computer programming? We can use the matrices to help us solve the system of linear equations, which is included in the optimization problems. And also we can do backpropagation in neural networks by doing a lot of matrix operations. So we can get back the new weights of the network, okay? So let us see how we can implement the matrix operations in Jupyter Notebook. So suppose I have these matrices in the form of arrays, and then I'm able to show the content that is created for A, B, C, and D. Okay, so if you want to create a matrix, you can still use the numpy.array function, and you have to include two rows here, okay, the first row and the second row. And in this case, you will see that A will become a 2 by 3 matrix. So you have 2 rows and 3 columns, okay. By the same token, you can produce matrix B, C, and D, okay, as long as you will see this rectangular matrix would come back, okay. And then I can do the addition. subtraction and scalar multiplication of the matrices, okay. And then I'm also able to handle the matrix multiplication by using np.matmul function, okay. And then I put A as the first value and B as the second value. Then I'm able to get A times B, okay. And I'm also able to get the transpose of the matrix by using A dot T, okay. So I'm also able to get the transpose of A by using A dot T, okay. And I'm able to get the inverse of the matrix, which is a square matrix, by using the np.linl submodule. And then from this submodule, I can use the inv function to handle the inverse of a certain matrix called C. And also I can use the linear algebra submodule to obtain the determinant function here called det, and then I can put a matrix C into it, which is a square matrix, to get the determinant. So let me try to run the cell. Okay, you can see that if I have these matrices coming out, A, B, C, and D, I can just do the addition of the two matrices that have the same dimensions, okay. So I can add these two things together, and I can do the difference of the two matrices in this way, and I can get the scalar multiplication of A by multiplying every element in A by -2, okay. And I can also do the matrix product by multiplying A by B here, as long as I'm able to achieve the dot product manipulation for my corresponding row and column, okay. Okay, you can see that I'm able to get the inverse and the transpose in this way, okay. A is here, and the transpose is obtained by flipping the rows and columns. So I will have this answer, and the inverse of C can be evaluated by using the inv function in the linear algebra submodule, okay. And the determinant can be found by the det function in the linear algebra submodule, okay. Now let us talk about eigenvalues and eigenvectors. So what does it mean by these two terms? So for a matrix A, an eigenvector V can satisfy this relationship. A times V equals lambda times V equals lambda times I times V. So lambda here is a scalar quantity called the eigenvalue, and V here will become the eigenvector, okay. So an eigenvalue lambda would correspond to a separate eigenvector V, okay. So this is a bit abstract. Let us use a numerical example. Suppose I want to find out the eigenvector and the eigenvalues of this matrix, okay. So I can do it here. A times V equals lambda I times V, right? So I can do the manipulation to have A minus lambda I times V equals 0, okay. So this is the 0 vector, and this is the V vector, and this is the I here, and this is of course the A, okay. So when I do the manipulation, I can have this relationship to come out. So in order to solve for this system of linear equations, we can evaluate the determinant first, and I can equate the determinant of this part to be 0, okay. So for the 2 by 2 matrix determinant, we can use the formula which is AD minus BC to get this one out, okay. And then we can solve for lambda to get lambda equals 2 and lambda equals 5 respectively from this quadratic equation. And we substitute the two lambdas into this equation, A minus lambda I times V equals 0, okay. So for lambda equals 2, we have this one to come out. So when lambda equals 2, I put 2 to here, so that I will have this one to come out. And when we solve for V, we can have V equals that one. So S is a scalar quantity before the vector called an eigenvector. So -1 and 1 is the eigenvector, okay, and it can possess a scalar multiple before it. And for lambda equals 5, we have this system of linear equations to come out, and we can solve for V here, which is equal to T multiplied by 2 to 1. So T is a scalar quantity, okay. So after solving the system of linear equations, we have these two answers for individual eigenvalue, okay. So we have two different eigenvectors corresponding to different eigenvalues, okay. And these two vectors are actually the eigenvectors, okay? So the scalar multiple can represent any number. So it means that the basic eigenvectors are these two vectors, okay? And how can we apply the eigenvectors and eigenvalues into computer programming? We can use eigenvectors and eigenvalues in the data analysis. For example, in the principal component analysis, PCA, we have to find out the eigenvectors to help us reduce the dimensionality in the data. So we can use the eigenvalues to determine which vectors are more important in the data. So we can ignore some less important vectors to reduce the dimension in our data. And for the graph algorithms, we can use the eigenvalues to help us analyze the network structures, okay? So by the same token as data analysis, we can try to find out the most important pieces of data that should be included in the network, okay? And for physics, we can use eigenvectors and eigenvalues to handle the stability analysis in the simulations, okay? So how can we implement the solution of the system of linear equations, and how can we find the eigenvalues and eigenvectors on Jupyter Notebook? Let us see the code here. So I can use np.array to produce an array first, which is actually a matrix here. And then I can use EIG function coming from the linear algebra submodule of the NumPy library to help us get both the eigenvalues and the eigenvectors. So the way to find out the numerical answer to eigenvalues and eigenvectors is quite easy. So let me run it. So when we find out the eigenvalues, I have 5 and 2, okay? So this matrix is not the same as the one on the notes, because you can see that 4, 1 becomes the row and 2, 3 becomes the second row, okay? So it is not the same as that one. But by using the AD minus BC equation, I'm still able to get the same eigenvalues, okay? And for the corresponding eigenvalues, I'm able to produce the eigenvectors correspondingly. So the first eigenvector will correspond to lambda equals 5, and for the second eigenvector, I'm able to see that the corresponding eigenvector is this one. So they are normalized. And of course, when we multiply the scalar multiple differently to the eigenvectors, the values would be different. So we can say that the eigenvectors would not be unique. It just depends on the scalar multiple before the eigenvector. That's why the computer can represent the eigenvectors in different ways by changing the scalar multiple, okay? And number 5, let us talk about the linear transformations. So how can we do the linear transformations by using matrices? We can use the matrices to represent the transformations like rotation or scaling. How can we do so? Let us see the meaning of the linear transformation first. So a linear transformation is really a function that takes a vector as the input, and the linear transformation can output another vector. And the linear transformation is able to preserve both addition and scalar multiplication. So the word preserves here is meaning that thing. So when I put the sum of the two vectors into the transformation, I'm able to get the new transformation, which is equal to the addition of the separate transformation of the vectors, okay? So you see, separate transformation comes here, and then I add the two things together. The result will be equal to the transformation of the sum of the two vectors, okay? And the meaning of preserving scalar multiplication is something like this one. When I do C times U here, C is a scalar multiple and U is a vector, I'm able to do this transformation for the resulting vector, and the result will be just equal to the transformation of the vector first, followed by the scalar multiple, okay? So that is the meaning of the word preserves in this context by referring to the mathematical definition here, okay? And for every linear transformation, we just do matrix multiplication. So when we see the word linear transformation, we are just doing matrix multiplication. So how can we do the multiplication? Let us see here. If we want to do rotation, we can multiply the 2D vector by this one, this matrix. The word pre-multiply means that this matrix comes first, followed by the vector to be handled. So here, theta is the angle of rotation, okay? And for the scaling matrix, it is like that. If I want to scale the vector by different scale vectors along the x and y directions, I can just multiply the whole matrix by the vector to be manipulated. So I'm able to do the scaling and the rotation. So let us see the example here. If I want to do the rotation of the point 21 by 30 degrees calculated from the horizontal x-axis, I'm able to see that the new point here is just that one and that one. Okay, so I just do multiplication of the matrix and the corresponding vector to get this one as the answer. So I can transform this point 21 to another point, which is shown here. Okay, and if I want to do the scaling of 21 by 2 along the x direction and 3 along the y direction, I'm able to show that the matrix multiplication result would help us get this new point as the answer. So when I want to undertake scaling on this point 21, I'm able to return 43 as the answer. Okay. And how can we apply the linear transformations in computer programming? We can use it in graphics. So we can do the rotation or the scaling of objects in 2D or 3D space. Okay. For example, by using the OpenGL transformations. And for robotics, we can find out the coordinate transformations for the robot arm movements. So to move the robot arms, we need to do matrix multiplication. So let us see how we can apply the linear transformations on Jupyter Notebook. So here, I decide to do the rotation by 45 degrees, which is equal to pi over 4 in radian. So np.pi is able to get the pi value in the computer. And pi over 4 is just obtained by pi/4. Okay, so that is the theta of my transformation. And then I just input the transformation matrix, which is this one, to the computer. Okay, and then I can use np.cos and np.sin to represent the cosine function and the sine function. Okay. And then this theta is just obtained before, and this theta is put into the rotation matrix. And suppose I have the point called 10, I can do the multiplication by using np.dot here. So this is the matrix and this is the point. So as long as the dimensions are correct and they are matched, I'm able to do the multiplication easily. So for the scaling, I can put this sx here and xy here, so that I'm able to do the scaling of the point called 10, which is this one, to another value called the scaled point. So let's see the result. So you can see that when I do the rotation, I'm able to turn 10 to the other point. And if I want to do the scaling of the point 10 to another point, I'm able to show 30 as the answer. Okay, so I just turn 1 to 3 and 0 to 0 as well, because the scale vector of 2 along the y direction doesn't affect the 0 coordinate for the y part. Okay, so this video has discussed some properties of linear algebra that are essential for us to do the computer programming. So we have learned vectors, and we can do the addition, subtraction, or scalar multiplication and the dot product quite easily. And we can get the length of the 3D vector. And also we have learned something about matrices. We can handle the addition, subtraction, scalar multiplication, and matrix multiplication. After that, we can know how to get the inverse of the matrix, and we know how to get the determinant of the square matrix. Okay, and we also know how to get the eigenvalue and eigenvector if we are given the matrix. Okay. Finally, we are able to do the linear transformation by pre-multiplying a rotation matrix or pre-multiplying a scaling matrix. This is the end of the video. If you have any questions about my video, please leave your questions on the comment section below the video. If you like this video, please give me a like and please subscribe to my channel. Thank you for watching.